Welcome to course on strength of material, and we will begin with the general properties of a material. And let's begin with the Hooke's law. The Hooke's law. Stress is directly proportional to strain, and to remove this proportionality sign, the stress is equals to E epsilon. This is the stress, this is Young's modulus, and this is strain. A few important things: E for cast iron is half of E steel, and modulus of elasticity of aluminum is 1/3 times elasticity of steel. So what does this mean? That elasticity of steel is 2 times elasticity of cast iron and 3 times elasticity of aluminium. Now, what is the deflection? This is given by PL upon AE, where the deflection is P upon EA times L, that is P upon K, or K is equals to EA upon L, which is also the stiffness. Now, deflection of bar due to self weight. Due to this section, say dx, deflection is WL upon twice AE, or it is also equal to gamma L square upon twice E, where W is the weight of the beam, or the self weight. Gamma is the specific weight, that is weight per unit volume. Others L and is the length, and E is the Young's modulus of elasticity. Now for the conical bar, the above was the case for prismatic bar. Now we take the case of conical bar. Deflection is gamma L square upon 6E times is, or 1/3 of a deflection deflection of the prismatic bar of same length, okay, which was gamma L square upon twice E for prismatic bar, and this whole is for conical bar. Now deflection of tapered bar. This is your tapered bar with D1 and D2 diameter respectively, and P is the force acting. Okay, then the deflection in case will be 4PL upon pi E D1 D2. For rectangular tapering bar, and the other sections will not be visible this diagram, and we are focusing on the deflection, which is PL ln E or log times B2 upon B1 times ET B2 minus B1, where the length of this face is B1 and that of this face is B2. Clear? Equivalent Young's modulus. E equivalent is nothing new. A1 E1 plus A2 E2 is upon A1 plus A2. There all the is known. Now defining the Young's modulus of elasticity. E is longitudinal stress upon longitudinal strain. Next is modulus of rigidity, represented by G here, shear stress upon shear strain. Bulk modulus, represented by letter K. This is direct stress upon volumetric strain. Now comes the Poisson's ratio, which is most important and is very frequently asked in the examination. What is mu? Lateral strain upon longitudinal strain. Okay. Now this mu value is less than 0.5 but is always greater than 0. It is 0 for cork, 0.5 for perfectly plastic body as rubber, 0.5 for rubber, 0.25 to 0.42 for elastic metals, Next, 0.1 to 0.2 for concrete and 0.286 for mild steel. So the others are not that important, but this should be remembered. Now comes the volumetric strain. Epsilon V. Volumetric strain is epsilon strain in x direction, strain in y direction, and strain in z direction. So this is sigma x plus sigma y plus sigma z upon epsilon times 1 minus 2 mu under hydrostatic loading under the water submerged case. The stress will be same in all the three directions. So here sigma x plus sigma y plus sigma z upon sigma x is equals to sigma y is equals to sigma z for hydrostatic loading case, and here volumetric strain will be 3 times sigma upon E to 1 minus 2 mu. Now the uni-axial loading on rectangular parallelopiped epsilon x is delta L on L is sigma x upon E, epsilon y is B upon B is equals to minus of mu sigma x upon E epsilon z is delta D upon D is equals to minus of mu sigma x upon E. For triaxial loading on a rectangular parallelopiped, epsilon x is sigma x E minus mu sigma y on E minus mu sigma z on E is equals to delta L upon L. Similarly, epsilon y and epsilon z will be minus mu E times sigma x minus sigma y, and here sigma y upon E minus mu E times sigma x minus sigma z. Clear? Our next topic is volumetric strain. volumetric strain for cylindrical bar. So epsilon V is longitudinal strain plus 2 times diametric strain. Now volumetric strain in sphere is 3 times diametric strain. Clear? Now we have some relationship. E is equals to 3k times 1 minus 2 mu. E is 2g times 1 plus mu. Next is E is 9 kg upon 3k plus g, and mu is 3k minus 2g upon 6k plus 2g. And here it should be noted that for homogeneous and isotropic material, the number of independent constant elastic constant is 2, for orthotropic is 9, and for anisotropic is 21. Now the strain energy, which was U is equals to half T theta in the case of cylinder and sphere. Here also it's same, and also half P delta, where P is the applied load, delta is the elongation due to applied load, T is the torque applied, and theta is the angle of twist. Now what is resilience? The resilience is the area under P delta curve, load and deflection curve, is equals to P delta curve area, and it is nothing but resilience is half times P delta. Proof resilience. The maximum energy absorbing capacity of the material in elastic region is proof resilience. Half P in the elastic limit times the deflection in the elastic limit. This is the proof resilience. Now thermal strain. Thermal strain. So let's see for the thermal stress is given by E alpha T, deflection is L alpha T, strain is L alpha T upon L is alpha T. Now alpha steel is alpha concrete, both are equal, and is equals to 12 into 10 to the power minus 6. This will be given in the question itself. Degree centigrade. Alpha for aluminum is greater than that of brass, is greater than copper, which is further greater than steel. And there is no thermal stress in case of free bar. Hope you like the course. Do keep revising and keep solving the questions. We will meet in the next video. Till then, stay tuned, keep practicing.